Okay, now we're going to start Chapter 5, Gas Laws. This representation of the periodic table is to show you what gases, the ones in blue, or what elements, the ones in blue, exist as gases at 25 degrees Celsius and 1 atmosphere of pressure. So there aren't very many. This is a table of some gases or substances found as gases, also at 1 atmosphere, 25 degrees Celsius. Of course, the molecular elements are shown here, ozone, but also some substances. We're quite familiar with the fact that carbon dioxide and carbon monoxide are gases at 25 degrees Celsius, but there are some others here as well. So going back to chapter 3, the physical characteristics of gases. Gases assume the volume and shape of their containers. They are compressible, so we can compress them into smaller volumes. And if they are added to a container with another gas, they will completely and evenly mix together. They won't separate themselves from each other. And gases have much lower densities than liquids and solids. So standard atmospheric pressure is equal to the pressure that supports a column of mercury exactly 760 millimeters high at 0 degrees Celsius at sea level. Okay, 1 atmosphere equals 760 millimeters of mercury. So here are some relationships between these pressure units. We won't deal with pascals, but you will see these 3 units. 1 atmosphere again equals 760 millimeters of mercury, or 760 torr. The barometer is the most common instrument used to measure atmospheric pressure. And we have a reservoir of mercury here. And we have this column. And that's where we will have a scale that we can actually read the height of that mercury. And the atmospheric pressure pushes down on that reservoir, and the mercury is at some level within that tube. So this is an apparatus that is also used to measure pressure of gases other than at atmospheric pressure, or the atmospheric pressure. So we have 2 different kinds, an open and a closed. The closed is used to measure pressures below or less than atmospheric pressure. So this is the closed manometer. There's a vacuum here. We have a column of mercury, and we have a gas in this container. And the pressure that this gas exerts on that mercury can be measured by taking the difference in the height of this side of the mercury and that height of the mercury. So this is a direct measurement of that gas pressure. So P of the gas, pressure of the gas, equals P of the height. So this is the height. The open manometer is used to measure pressures that are greater than atmospheric pressure. And in that open tube, the height difference represents the difference between the pressure of the gas in the flask and the atmospheric pressure. So when the pressure of the gas is greater than atmospheric pressure, the level in the arm attached to the tube is lower than the level of the arm exposed to the atmosphere. So this is the P of the gas, then can be calculated by adding or summing the P height to the atmospheric pressure. So a gentleman by the name of Boyle used U-shaped tubes to study the relationship between pressure and volume of a gas. And the volume of the gas in a closed end of the tube changes in proportion to the difference in the height of the mercury columns as mercury is added to the open end of the tube. So these ends are open to allow for the addition of that mercury, and we can compare A to B to C. Here we have this amount of mercury and our volume of gas is 100 mils. However, when we increase that amount of mercury to 760 millimeters, we decrease our volume to 50 milliliters. And if we increase that pressure from the mercury column further, we further decrease that volume of gas. So as pressure increases, volume decreases. So we can plot these relationships. And the graph on the right is P showing its, I'm sorry, that should have been on the other side over there. This is reflected over here. This is the actual graph, but so this is pressure versus volume, we see that decrease, but we also have a curved line here. If we plot the inverse, we get this nice straight line. So this indicates there is an inverse relationship between pressure and volume. So because of this, we can say that P times V equals a constant because there's proportionality there. And we can also expand this and say P1V1 equals P2V2. And this is called Boyle's law. So we do have constraints here, and those constraints are that this law applies when there is constant temperature or no change in temperature, because we know that volume can change with increasing temperature or decreasing temperature, and a constant number of moles of that gas. So how do temperature and volume relate? Here we have two capillary tubes. We also have mercury here and a gas in the bottom below that mercury. And at low temperatures, that volume is small. But if we increase the temperature, so we're increasing the kinetic energy of that gas, it is going to expand and the volume increases. So this indicates that temperature is volume is directly proportional to temperature, which leads us to Charles' law. And Charles is the individual who studied the relationship between volume and temperature. As temperature increases, volume increases. Here's a plot or a graph of some different pressures noted here, and volume. Well, we're plotting volume versus temperature, but these, I called that pressure, and I don't know why I did. The use of P makes me think pressure, but pressure is constant. These are actually different volumes and temperatures, but what's important here is where these, if you extrapolate this data down to the x-axis, they all merge at negative 273.15 degrees Celsius, which is what? 0 Kelvin. So because of this relationship with temperature, all of our gas laws that involve temperature must use temperature in Kelvin. So V is proportional to T. So that means V equals some constant times T. And we can expand that to determine a second volume and or temperature based on initial conditions. So V1 over T1 equals V2 over T2. Keep in mind, temperature must be in Kelvin, always, for any gas law work that involves temperature. Another law that we're going to look at is called Avogadro's law, and this relates volume and number of moles. So there is a direct relationship between volume and number of moles. So volume equals a constant times N, or the number of moles. And we can also expand that and have initial and final conditions and use this relationship just as we've seen with the other two laws. This constraint is constant temperature and constant pressure. So this leads us to the ideal gas equation, which is a combination of Boyle's, Charles, and Avogadro's laws. And I will actually, when we work some problems in the next video, derive this for you. But here is an example of that, or the representation of that. Boyle's law, volume is proportional to 1 over P. So these have all been arranged. So we have V on the left side of this relationship. Charles' law, V is directly proportional to T, and Avogadro's, V is directly proportional to N. So if we can combine these and say V is proportional to NT over P. So that means that we have a constant, and that constant for this gas law is going to be called R. It is the gas constant, so we call this the ideal gas constant. And that gives us the ideal gas equation, PV equals nRT. So there's another characteristic of gases, and that is molar volume. But before we look at what molar volume is, we need to define what standard conditions are. And standard temperature and pressure are 0 degrees Celsius and 1 atmosphere. So STP, standard temperature and pressure. And experiments have shown that at standard temperature and pressure, or STP, 1 mole of an ideal gas occupies 22.414 liters. Doesn't matter what the identity of that gas is. If it behaves ideally, and all gases do at STP, then it will have a volume of 22.4 liters. We typically shorten it to 22.4. So how did we arrive at R? We know, or we have this ideal gas law, PV equals nRT, but how did we find R? We can rearrange that equation and solve for R. And this is at STP. So at STP, pressure is 1 atmosphere. Experimentally, we've shown, or it has been shown, the volume is 22.414 liters. This is for 1 mole of gas at 273, 0.15 K. 0 degrees Celsius is 273.15 K. And that gives us our ideal gas constant, 0.082057. We typically round this to 0.0821. So point 0.0821. You should know that number. The units here are liter atmospheres per mole K. It's very important to include those units now, especially working with all these, with 4 units in 1 constant. So there are a couple of other relationships that we have been able to derive, and again, when I do make the next video and I work some problems for you, I will show how these relationships are derived, but I'm just showing the equations here. Density equals mass divided by volume, okay? And we can also utilize density and molar mass in what's the word I'm grasping for, in a derivative, let's say, of the ideal gas constant. Masses, m here, of course, is the mass of a gas in grams, and m is a molar mass. So if we have mass and molar mass, we can determine moles. But density then equals P times the molar mass over RT. And the molar mass of a gas can be calculated or determined by density times RT divided by P. And density of gas, if you recall, is given in grams per liter. If you think back to our initial discussion of density, liquid densities are in grams per mil. Solid densities are typically given in grams per centimeter cubed, and gases in grams per liter. And next up, we'll do some problems, and I'll show you that derivation of the ideal gas constant before we move on to other gas topics.